All right, kids, it's time for discussion 2.1, spectral analysis of atomic structure. Basically what this discussion is all about is the modern evidence we have for the structure of atoms. So we're going to look at 4 different spectra. Spectra, of course, is just the plural version of the word spectrum. So we're going to look at mass spec, emission spectrum, absorption, and continuous spectrum. All right, we'll look at it all at once. So let's first talk about mass spectrometry. So this is actually a device that is used to identify unknown compounds and elements. And it tells us what we're looking at by telling us what the mass data is. So how this device works is a sample is put into it, and the sample is zapped with X-ray radiation. That does 2 things. It first vaporizes the sample, and what that basically does is separate its components into different bits. So like if you have a metal or something, it'll get separated into the atoms, individual atoms. And it also ionizes it. So we knock an electron off from the structure. So once we have these gaseous ions, they're accelerated through an electromagnet. Because they're charged, they'll be deflected by that magnet, with the lighter bits being deflected more than the heavier bits. So everything is essentially separated based on mass to charge ratio. Now mass to charge ratio you'll see written out as m/z. If you recall from physics, lowercase z is how we refer to electrical charge. Now what you see is a graph with an x and a y axis. You'll see a series of peaks where the location of the peak on the x-axis will show you what the mass to charge ratio is. Now, everything gets what's known as a unipositive charge. So all of the fragments have the same charge. So essentially what you're seeing on the x-axis is just the mass of each component. The height of the peak will show the relative abundance. So basically these things are separated by their masses. Each atom or molecule hits a detector. The more times it hits the detector, boop, 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 the higher the peak will show in the spectrum. So relative abundance will show us the percentage of each component. So if I put, say, a sample of rubidium into the mass spectrometer, what it's going to show me is all the different isotopes of rubidium. They'll all be separated by their masses. It'll also show us their natural abundance. When I see something that gives me mass data and something that gives me abundance data, it makes me think of one formula, and that is the formula for calculating relative atomic mass. So, if you've ever wondered, how do we know about all of the isotopes of uranium or any other element? We know about them because of mass spectrometry. So let's assume we take a piece of rubidium and we chuck it in the mass spec. What we're going to see is 2 peaks in our mass spectrum, one showing a mass of 85, the other showing a mass of 87. That means that the mass spec is telling us that rubidium has 2 isotopes. Now, in order to get the abundance, we have to basically look at the height of the peak and determining what portion of the total is the height of that peak. So basically what we got to do is just measure the height of each peak. So if I did measure with a ruler, if I found the length of that to be 1, what you'd find when you measured this one is that that one is actually 1/2. So in order to use these heights as percent data, what we need to do is take the height of each peak and divide it by the total height of both peaks. So part over the whole times 100. So when I plug into my relative atomic mass formula, it's going to be the mass of rubidium-85 times the height of its peak over the total height, plus the mass of rubidium-87 times the height of its peak over the total. When we actually plug the values into the equation, we get 85 times 1 over 1.5 plus 87 times 0.5 over 1.5, and we get 85.67. If you look at the periodic table, I've got one right here. It says that rubidium has a relative atomic mass of 85.47. So we're off by 2/100ths, but this is still pretty close. All right, so what do we mean when we say relative atomic mass? Anything that is a relative quantity is just a quantity that's based on some standard. So all of the relative atomic masses we see are based on the AMU, or the atomic mass unit. And all those atomic mass units are based on one atom of carbon-12. So the old way to determine the relative atomic mass of an element was by taking the mass of a single atom of that element and dividing it by 1/12 the mass of a carbon-12 atom, and that would give us the relative atomic mass. Nowadays we use the mass spectrometer. It's much more better. Sorry, I wanted to avoid the bell. But what do you guys need to know? Really, in 7 years of teaching this content, the only evidence I've ever seen for something that the IB wants you to know is what the standard is. So if you're asked, what is the standard used to determine the relative atomic masses of all elements, and all you got to know is that it's carbon-12. Carbon-12 is the standard. All right, so let's go ahead and look at the electromagnetic spectrum. I see, when I look at the electromagnetic spectrum, I see different types of electromagnetic radiation: radio, microwave, infrared, visible, UV, X-ray, and gamma. I can see that the electromagnetic spectrum goes from low energy to high energy. So as we move from right to left, our radiation increases in energy. I also see that this is arranged in order of wavelength. And the wavelengths from right to left go 10 to the 12, 10 to the 10th, 10 to the 8th. They're getting smaller. So gamma has more energy and a shorter wavelength than X-ray. If we look at the lower end of the spectrum here, we see that this is also a spectrum of frequency, where the frequency of radiation is increasing 10 to the 4th, 10 to the 6th, 10 to the 8th, and so forth. So the overarching trend here is that the smaller the wavelength of your radiation, the higher the frequency will be, and the more energy the wave will possess. So if I wanted to look at wavelength, if I compared two waves, wavelength is the distance between peak to peak or trough to trough. So I would say that this wave down below has a longer wavelength. Now frequency is defined as the number of peaks that pass a predefined point in space in 1 second. So since all of this radiation moves at the same speed, the speed of light, a shorter wavelength will equal a higher frequency. Now the most important bit of this is that visible light exists on this spectrum, with red light being at the low energy end of the spectrum and blue and violet light being at the high energy end of the spectrum. So we could say that a particular wavelength of light is equal to a particular energy. All right, so we can actually calculate the energy of radiation using a handy-dandy pair of equations. E equals h nu, or E equals hc over lambda. Now let me go ahead and define all these terms. E is just the energy of radiation. H is something we call Planck's constant. And the value of Planck's constant is 6.63 times 10 to the negative 34th joules times seconds. You do not have to memorize that value. It is in the data booklet. Nu is the frequency of radiation, and frequency is measured in inverse seconds. H is still Planck's constant. You should know from physics that c is the speed of light, which is equal to 3.0 times 10 to the 8th meters per second. And lambda is the wavelength of radiation, which is measured in nanometers, or 1/1000th of a meter. So these are essentially just plug and chug problems. If you're given frequency and asked to calculate energy, it's just Planck's constant times the frequency. If you're given the wavelength of radiation and asked for the amount of energy it contains, H and C are constants, so all you would need to know is the wavelength to solve for the energy. So take a look at this first problem, pause the video, and see if you can work it out. All right, so in this case, we're given a frequency. So I'm going to be using the very first portion of this equation, E equals h nu. That, by the way, is not the letter V, it's the Greek letter nu. So all I have to do is plug into my equation, Planck's constant times frequency. You can see here that seconds cancel, and I'm left with 6.63 times 10 to the negative 26th joules. Now I want to say a little thing about this next one before you actually start it. Whenever you're given the wavelength, wavelength is always reported in nanometers. Now, if we're going to be using this equation to calculate the energy, we're going to be taking the speed of light and dividing it by the wavelength in order to get joules. So the speed of light is measured in meters per second. Oops, I didn't mean to erase that. And wavelength is in nanometers. So before you do the calculation, you have to make sure that all of your units are consistent. The easiest thing to do is to convert the wavelength from nanometers into meters. So a nanometer is 10 to the negative ninth meters. So if you're given nanometers, to convert it into meters, all you have to do is take whatever value you are given in nanometers and drop it times 10 to the negative ninth after it. So go ahead and with that in mind, see if you can solve this problem. Alrighty, so when we put up the work, since I'm given wavelength, I have to use hc over lambda, Planck's constant, speed of light, wave divided by the wavelength in nanometers, seconds cancel, meters cancel, because it's divided by meters, okay? And I get 2.84 times 10 to the negative 19th joules. I typically don't see these problems asked by the IB because they tend to avoid plug and chug style problems, but there's a first for everything. All right, so now let's look at the different type of spectra. First is a continuous spectrum. A continuous spectrum is produced when white light shines through a slit and a prism. What you get is a full rainbow. In a continuous spectrum, all wavelengths of light are shown in the spectrum. This is the spectrum we see when we pass sunlight through a prism or rain through a prism. Right? Now, when the source of your radiation is the sun, you'll get a continuous spectrum, but if we have a different source of light, we can get a different type of spectrum. So an emission spectrum is the spectrum that is produced when individual elements are irradiated. We add energy to individual elements. That causes those elements to emit light. When we look at that light source and pass it through a prism, we do not get a continuous spectrum. What we get is the emission spectrum, which looks like this. It's a black background with individual lines of color. The lines of color in the spectrum represent, actually I'll talk about what they represent in a subsequent slide. So, all right, so this is the hydrogen emission spectrum. I see we have one red line, a light blue, darker blue, and a violet line in the spectrum. So how do these lines get produced? Well, when energy is put into an individual element, that energy is absorbed by the electrons. That causes the electrons, since they absorbed energy, to move up to a higher energy level. We call this the excited state. Now, this is not a stable arrangement for this atom, and that electron eventually is going to fall back down to a lower energy level. It absorbed energy to move up, so in order to move back down, it has to give off energy. That energy is given off in the form of visible light and will show up as a line in the emission spectrum. So what's the significance of this? Well, the fact that we only see individual lines in the spectrum tell us that only certain transitions are possible for electrons. So just to draw this out here, if we looked at a Bohr model of an atom, if that red dot is the nucleus, what we're saying is that electrons can live in those energy levels, but they cannot live in between. So the changes in energy between those energy levels will only produce certain wavelengths of light. In contrast, if the electrons could move wherever they wanted, one thing that's important to remember is that if you have a sample of matter, there are gajillions of atoms in that sample. So essentially, if the electrons could move anywhere, you would have an infinite number of possible electron transitions. If that were the case, you would see a continuous spectrum. The fact that we see an emission spectrum tells us that only certain transitions are possible. This is actually our evidence for the existence of energy levels around the nucleus of an atom. So you can also see here that the lines get closer together as we move toward the higher energy end of the spectrum. This is known as convergence, and we say that the lines converge at the higher energy end of the spectrum. Now, this actually makes a lot of sense when you think about the nature of atoms and electrostatic attraction and repulsion. So opposites attract. The nucleus is positive, the electrons are negative, so they attract each other. Energy has to be absorbed by that electron to make it jump to a higher energy level because it essentially has to break that force of attraction between itself and the nucleus. Well, as the energy levels move further and further and further from the nucleus, the grip that the nucleus has on those electrons is decreased. That means it doesn't take as much energy to promote the electron to another energy level, so we actually see the energy levels themselves getting closer together, and that's also why the lines get closer together. Whoa, cool. All right, so one thing you're going to have to produce is an energy level diagram. An energy level diagram is just a plot that shows all possible electron transitions around an atom. So what you're going to do is draw a horizontal line for each energy level. Looking at the periodic table, I see there are 7 periods. So we're going to draw a line for 7 different energy levels. I'm going to go ahead and label each one. So n equals 1 is the first energy level. When you draw the second energy level, leave a good bit of space between the first and the second. Every single energy level I draw, I'm going to draw a little bit closer to the one that came before. So 1, 2, 3, 4, 5, 6, 7. So n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, and n equals 7 at the top. You're then going to draw one more line a little bit further up and label it n equals infinity. So using an energy level diagram, we can show the movement of electrons. We can show them jumping up and jumping back down to different energy levels. And we'll show the application of this in a couple more slides. And of course, there is the definition. It's just a plot that shows the spacing of electrons in an atom and all possible electron transitions. Okay, so electrons go up, and when they pop back down, they release electromagnetic radiation. Depending on which energy level those electrons land on, they're going to produce different frequencies of radiation. So if we look at an electron that is in the excited state that falls all the way back to n equals 1, the series of lines that you'll see in the emission spectrum for that transition will be in the ultraviolet region of the spectrum. So they'll be off over here in the area of the spectrum where we can't see them. Different transitions produce different types of radiation. So transitions to n equals 1, like we just said, will appear in the ultraviolet region of the spectrum, and we call those lines the Lyman series. Now don't worry too much about the names of the series. You don't need to know the names, but you do need to know the type of radiation that will be released for a particular transition. So transitions that terminate at n equals 2 are called the Balmer series, and most of those lines will show up in the visible region of the spectrum with a little bit in the ultraviolet. And transitions to n equals 3 are called the Paschen series and will appear in the infrared region of the spectrum. All right, so let's go back to the energy level diagram. So what you're going to be asked to do is show the series of lines that could be produced, the series of lines that represent the transitions that could produce a certain type of radiation. So 1, 2, 3, 4, 5, 6, 7. Gets tough to label when they get close together. All right, so I know that if an electron goes from an excited state all the way to n equals 1, then that will release ultraviolet radiation. So the series of lines in the energy level diagram will essentially show us all the possible transitions that could produce ultraviolet. So I could have an electron start at n equals 7 and go to n equals 1, or it could start at n equals 6 and go to n equals 1, or n equals 5 to 1, 4 to 1, 3 to 1, or 2 to 1. All of those transitions will release radiation in the ultraviolet range. If I were asked to show the possible transitions that would produce visible light, transitions that terminate at n equals 2 produce visible light. So an electron could go from 7 to 2, 6 to 2, 5 to 2, 4 to 2, or 3 to 2. These would be the series of lines that could produce visible light. If I were asked for the series of lines for infrared, it's just showing all possible transitions that terminate at n equals 3. So those arrows represent the series of lines that could produce infrared. Moving right along. Okay, so let's turn back to n equals infinity. In fact, actually, let me remember to write my n equals infinity line. All right, so recall the definition of ionization energy. Ionization energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous phase. So basically, it's the amount of energy you got to put into an electron in order to take it away. So far we've been talking about the amount of energy that's required to promote to a higher energy level. N equals infinity represents the amount of energy required to completely remove the electron from the atom. So understanding that concept makes this problem significantly easier. Let me show you what I mean. In a given atom, it is said that an atom is ionized, it loses an electron, when it reaches its convergence limit, n equals infinity. And looking at the lines in a Lyman series, this would be the line with the shortest wavelength. For a particular atom, the shortest wavelength line in the Lyman series is 91.16 nanometers. Calculate the first ionization energy of this atom. Essentially what this is saying is that 91.16 nanometers equals the energy required to remove the electron. Well, if you're given the wavelength of radiation, we know how to calculate its energy, hc over lambda. So we're going to plug our values into the equation. 6.63 times 10 to the negative 34th times the speed of light, which is 3 times 10 to the 8th, divided by the wavelength. Don't forget, 91.16 is in nanometers. Put your times 10 to the negative 9th afterwards to turn it into meters. When you solve, you're going to get 2.18 times 10 to the negative 18th joules. Now this says in a given atom, so that's the number of joules per atom. Typically, ionization energy is in kilojoules per mole. So what I want you guys to do is pause the video for a second, see if you can make the conversion, converting joules into kilojoules and atoms into moles. All right, so let's work on one conversion at a time. First of all, to convert joules into kilojoules, I have to divide by 1,000. To convert atoms into moles, I have to multiply by Avogadro's number. You can look at what happens to our units when we do this. Joules cancel, kilojoules don't cancel, which is kind of what we're looking for, sorry. I'm being a little rapid there since this is the third time I've tried to record this video in the last 2 days. And atoms cancels with atoms, and we're left with kilojoules over moles. And we get 1.13 times 10 to the third kilojoules per mole. All right, last type of spectrum is called an absorption spectrum. The absorption spectrum is the one that's being used most now in the modern age to discover things about our universe. So how does it work? When light passes through a hot gas, some wavelengths of light will be absorbed by the gas. So when we pass that light through a slit and a prism, what we see is a spectrum that's mostly continuous, but with black lines. The black lines represent the frequency of light that had been absorbed by the gas. So different gases, different elements will produce different absorption spectra. So what are the uses of this? One, any colored thing will have an absorption spectra. Right? So you can use the absorption spectra if you're able to vaporize the substance and pass light through it. You can look at the absorption spectrum and identify what it is. The coolest thing I think that absorption spectra are being used for is to actually analyze the atmosphere of exoplanets. So exoplanets are planets in other solar systems. And when an exoplanet passes in front of its host star, if it has an atmosphere, the light from that star shines through the gases in the atmosphere. That light, hopefully, will eventually make it all the way to Earth. When it does, we can look at the absorption spectrum of it and determine which elements are present in that atmosphere. So when they say a planet 20 million light years away, or 20,000 light years away, excuse me, they can tell that it has water vapor in its atmosphere. We know that because we see the absorption spectrum for water in the spectrum of the light from its atmosphere. Another use of the absorption spectrum a long time ago was determining the composition of the sun. So helium is a very light gas. It's so light that any helium on the surface will fly off into space. So all of the helium that we've ever used on Earth comes from the radioactive decay of uranium in the Earth's crust, alpha decay. Remember, an alpha particle is the nucleus of a helium atom. So when the first time that the light from the sun was analyzed by looking at its absorption spectrum, all the usual suspects that were expected to be found were found in the spectrum. However, there was one element that nobody had ever seen in an absorption spectrum before. They decided to name that element helium based on the Roman god of the sun, Helios. I think that's very cool. But in any case, absorption spectra are at the cutting edge of science and technology. Okay, so that's it for the discussion. Hopefully that was clear. If you have any questions, please bring them to me in class. Thank you so much, as always, for watching, and have a wonderful day.